Good morning, everyone. Good morning, everybody. I'm sorry that I'm not here today, but what I'm going to go ahead and do is I'm just going to have this YouTube video up, and we're just going to go through the lesson like normal. So what I want you to do, go ahead and take out your homework assignment, and we're going to first start off by checking the work, okay? So here's the answers, problems 8 through 26. If we could just go ahead and pause the video now and allow the students to check their work. Once you're done with that, we'll go on to the next section. Here's 28 through 32. Once again, you can pause it for the students to check. All right, great. Now, students, if you have any questions on those, we can go over the questions on Monday when I see you again. So let's get into the lesson for today. The lesson today is 9.2 exponential functions. All right, now once again, you guys can pause this video whenever you need to, but I'm going to kind of go through it pretty rapidly just so that the video isn't too long in length. All right, so first, let's start off. Exponential functions. Exponential functions are similar to functions that we've seen before, except for the one thing. Here, we notice that the exponent in an exponential function is a variable. Okay? So, the difference is that in an exponential function, the exponent is a variable. Quadratics, we always in a quadratic had a highest exponent of 2. Or even in a cubic, we had a highest exponent of 3. But in an exponential function, the exponent is a variable. All right, don't need to worry about writing any of this slide down either. The table and the graph show an insect population that increases over time. We notice that from time at the beginning, from 2 to 6, we increased by multiplying by 3, and we multiply by 3 in every time element in the table. Okay? Now, the function that describes this pattern is f of x equals 2 times 3 to the x. This is an exponential function because the variable is an exponent. Notice that 2 here is our starting point. And 3 is the ratio between the values. Okay, so this is what an exponential function looks like. 2 is our starting point, and 3 is the ratio between the values. All right, meaning that we multiply by 3 to get to the new elements in the table. All right, now I do want you to write this down. Exponential functions. Exponential functions are in the form y equals a times b to the x, where a can't be 0, b cannot be 1, and b has to be greater than or equal to 0. All right, so let's go on to the first example. Go ahead and write down what's underlined. Example 1, the function f of x equals 500 times 1.035 to the x models the amount of money in a certificate of deposit after x years. How much money will there be in 6 years? All right, in this problem, all we're going to do is we're going to take our values and we're pretty much going to just plug them in, okay? So they gave us this function, and the first step is to write it down. After that, we're finding out how much money will there be in 6 years. So we're going to take 6 and we're going to plug it in for x. Okay? Now, this f of x equals 6, this part right here, don't worry about that. All that means that is we are evaluating this function at year 6. Okay, so honestly, you don't even have to have it there if you don't want to. All we're really doing is plugging in 6 for x. All right, and when you plug in 6 for x, you get out, let's see here, you get out 614.627. And I'm going to go ahead and just round that to $614.63. Okay? All right, let's go ahead and do this one. Now, I would like you to pause this video right now and allow the students to try this on their own. All right, so the function f of x equals 200,000 times 0.98 to the x, where x is the time in years, models the population of a city. What will be the population in 7 years? All right, so we're going to take our function once again, f of x equals 200,000 times 0.98 to the x. And we're evaluating this at time 7. So we're just going to plug in 7 for x. So that comes out to be, I missed my 7 there. That comes out to be 173,625 people, approximately. All right, I'm going to round to the nearest whole number because you can't have part of a person. All right, great. Let's go on to the next. Remember, linear functions have constant what? They have constant first differences. Okay? Go ahead and write that down. Linear functions have constant first differences. Now, just to kind of illustrate what we're talking about, remember when we did our tables before, a linear function has a constant first difference. When I graph this table here, it will make a line. All right? And the first difference is, well, we see that from here to here, we increase by 2. From here to here, we increase by 2. Increase by 2 here, increased by 2 here. So this function is linear because we know that this has constant first differences. All of those values are the same. Also, once again, you could check it by graphing, and this would make a line. All right, so quadratic functions we know have what type of differences? Constant second differences. Good. And once again, here's a quadratic table. If I was to graph this, it would be a parabola, but you could check it by looking at the differences. From here to here, we increase by 2. Here to here, we increase by 6. Here to here, we increased by 10. Here to here, we increased by 14. Okay, so those are the first differences. The second differences then, from here to here, was an increase of 4. Here to here was an increase of 4. Here to here was an increase of 4. Okay, so because the second differences are all the same, we know that this is a quadratic function. All right, now, exponential functions do not have constant differences at all. They have constant ratios. Please write that down. Exponential functions do not have constant differences at all. They have constant ratios. All right, so for example, here's a table, and you don't need to write down the table. Don't write down the table, but this table illustrates a exponential function. One thing that you always need to check when you're dealing with these is making sure that the x's constantly increase by the same rate. Just like we did in the linear, all the x's here increase by 1. In the quadratic, they all increase by 1. So here, they all increase by 1 also. Now, they could all increase by another number, like 2 or 5 or whatever, but they need to all increase at the same rate. All right? Now, in the exponential function, once again, they have constant ratios. So notice here, from one row to the next, we multiply the f of x, the y values, by 3. Okay, so that's a constant ratio. So we know because these are all multiplied by the same number, they have a constant ratio, and therefore they are exponential functions. This table represents an exponential function. Okay, let's get out of that. All right, so here, tell whether each set of ordered pairs satisfies an exponential function. Explain your answer. So what you would do here is start off by making a table. So we know the x values are 0, 1, 2, and 3. So we'll put those in, 0, 1, 2, and 3. And then the y values are 4, 12, 36, and 108. Okay, now, once again, always check and make sure you're increasing by the same thing in your x values. And we are. Okay, they're all increasing by 1. And then find out what's the value that you can multiply by to go from one value to the next. From 4 to 12, we multiply by 3. From 12 to 36, we multiply by 3. And from 36 to 108, we multiply by 3 as well. So therefore, because you had a constant ratio from one term to the next, this is an exponential function. So yes. All right, could you please pause the video and allow the students to try this one on their own? All right, so here we go. The x values in this problem, -1, 0, 1, and 2. So let's put those in. And the y values, -64, 0, 64, and 128. So -64, 0, +64, and 128. All right, so let's check the x values first again. So from here throughout the table, we notice that we're increasing by 1. So that checks. Now, what number did you multiply by to get from -64 to 0? Well, you had to multiply by 0. What number did you multiply by to get from 0 to 64? Yeah, there is no number. You can't even do that. All right, and from here to here, we multiply by 2. So because these are not the same, we know this is not exponential. Okay? Now, some of you might be able to tell me what type of function this actually is. What function is it? This actually is a linear, because from here to here, we added 64. From here to here, we added 64. And from here to here, we added 64. So the first differences are the same. This is a linear function. Not exponential, but linear. Okay? All right. Now, how to graph an exponential function. A couple steps, and once again, pause the video when you need to. First step to graph an exponential function is make a table. You're going to make a table of values using positive and negative integers for x. I would suggest just using -2, -1, 0, 1, and 2 for x. After you do that, you're going to plot the table. And then you're going to connect the points with a smooth curve. All right, so here we go. Example 5, graph y equals 3 to the x. So we're going to make a table of values. So once again, I would suggest you use -2, -1, 0, 1, and 2. You want some positive, some negative, and you want 0 in there. So just go ahead and use those. And then we're just going to go ahead and plug these values into our calculator. So we're plugging in 3 to the -2nd, 3 to the -1st, 3 to the 0, 3 to the 1st, and 3 squared. If you type in 3 to the -1st or -2nd in your calculator, the value you get out is 0.1 repeating, or 1/9. 3 to the -1st, that's 1/3, or 0.3 repeating. 3 to the 0 is 1. 3 to the 1st, that's 3. And 3 squared is 9. Okay. Now, after you have those values, you're going to take those and plot them. So let's start off. We're at -2, 1/9. Now, here's -2 on the x values. And then you're going to go up 1/9. Now, 1/9, that's a really small number. It's just a little bigger than 0. So we're not going to go up that far from the x-axis. -1 1/3, that's our next point. -1 1/3. We're going to go to the -1 on the x-axis, and then we're going to go up 1/3 of the way. So I'll say that's about here. Okay? Once again, those are just really small. Now, I am not going to be sitting there measuring these with a ruler saying, oh, they were a millimeter off, they get points off. No, this is all just an approximation. All right, let's go to our next point, 0, 1. Here's 0 for x and 1 for y. Our next point, 1, 3, that's here. And the next point, 2, 9, that is here. Okay, and now we go ahead and connect this with a smooth curve. All right, now, pay attention to how this curve looks. Notice that my curve never, ever will touch the x-axis. It never will get low enough to touch it. Okay? No matter how negative you get on the x values, there is no number that you can plug in for x up here to actually make it equal to 0. So it never touches this line. It never touches the x-axis. So please be careful and make sure that you do not allow your exponential graphs to touch the x-axis. Okay. In fact, the x-axis is called an asymptote. Write that down. An asymptote. An asymptote is a line that the graph gets closer and closer to, but it never touches. It's a line that the graph gets closer and closer to, but it never touches it. All right. Once again, like in the last problem, the x-axis was the asymptote. Whoops. X-axis was the asymptote because our graph will never touch this line. It'll get closer and closer to it, but it will never touch it. Okay? That once again is called an asymptote. All right, let's go ahead and do this one. Same premise here. You're going to pick your x and your x values, and you're just going to plug those in. So again, I would suggest you use -2, -1, 0, 1, and 2. And then you're just going to go ahead and plug in values. Okay? So when you plug in -2, you get out +1/8. -1 gives you 1/4. 0 gives you a half. 1 gives you 1. And 2 gives you 2. All right. So let's go ahead and plot those. -2, you're at 1/8. Okay. Once again, that's going to be really, really close to 0, but not quite there. So I'll just put that about there. All right. All right, let me just move it up just a little bit, just so that people don't think that I'm on my x-axis. -1, you're at 1/4. So you're going to go a fourth of the way up between 0 and 1. So I'll say that's about here. At 0, you're at a half. At 1, you're at 1. And at 2, you're at 2. Okay? So this one is a curve still. All right, this is still an exponential curve. Okay? We just really can't, it's not curved as much. Okay? I'm going to take this out just so that you guys don't think that that's touching. Okay? So there's our exponential graph. Great. All right, take a moment. Let's go ahead and pause the video and try this one on your own. All right, so once again, you're going to do your x and y values. Pick -2, -1, 0, 1, and 2. And when you pick those values, your corresponding y value should be, when you plug -2, you should get out +4. -1 is 2, 0 is 1, 1 is a half, and 2 is 1/4. Okay, so let's plot those. -2, 4. -1, 2. 0, 1. 1, a half. And 2, a fourth. Okay, so let's go ahead and connect with a smooth curve. All right, once again, our graphs are going to be asymptotal to the x-axis, so therefore it should never touch it. Okay, and be careful too, because I have a lot of students that will do something like this. They'll make their curve, and then like while they're doing the curve, all of it will be right, and then for some reason they start going up. All right, this is not a parabola. This is not a parabola, so you cannot curve this. Okay, it has to keep going down to closer to the x-axis. All right, let's try this last one. I believe this is the last one at least. All right, so here we have our x and y values. You're going to pick once again -2, -1, 0, 1, and 2. Now, be really careful here when you're plugging this in your calculator. All right, notice that this -4 is not in parentheses. Okay, so this is really the same thing as -1 times 4 to the x. These are the same equation. Okay, either one. But that 4, that exponent, is only attached to the 4. It is not attached to the negative. So if I was to plug this in my calculator, when I plug in -2, the value that I get out is 1/16. Excuse me, -1/16. When I plug in -1, I get -1/4. 0 gives me -1. 1 gives me -4. And 2 gives me -16. All right, so let's plot those. -2, -1/16. Now, here's -2 on my x-axis. Now, I'm going to go just a little below that for -1/16. Okay? Now, also, notice that I counted by 2's here because I didn't want to have to do all that, do all those tally marks for -16. Okay, so -2, -1/16, -1, -1/4. Let's say that's about there. 0, -1, that's about there. 1, -4, that's here. And 2, -16, that's here. Okay, so now you're just going to connect your graphs once again with a smooth curve. Remembering that your graph is asymptotal to the x-axis, so it should not touch it, cross it, or even curve around. Okay, great. There's example 8. And this is your homework assignment. All right, please make sure that your homework is done on graph paper. Have an excellent weekend, and I will see you guys on Monday.